Hello guys, in the previous video I have discussed about the basics of data pre-processing and some of the steps to balance the diabetes dataset, and in this video I will continue with the further steps involved in balancing the diabetes dataset. Before moving forward, let's have a quick look over the dataset. You can see that the data is still not balanced, so we need to apply further steps of pre-processing. Also, in the previous video we have dealt with the target feature, that is the number of readmissions. I have already explained this feature in the previous video. Now let's proceed with the further steps of data pre-processing. We will drop some features which are irrelevant. So in this code we will be dropping some of the records. So as our dataset contains up to 3 diagnoses for a given patient, that is primary, secondary and additional. So diag 1 is primary diagnosis, diag 2 is secondary diagnosis and additional is diag 3. So diag 1, diag 2 and diag 3 have very few missing values, and if all the 3 values are missing, then that's bad data. So we will drop only those records in which all the 3 diagnoses are missing. So this is the code for that. Like wherever there is question mark at the place of diag 1, diag 2 and diag 3, so we will drop those records having question mark in all the 3 diagnoses. Again, since we are trying to predict readmissions, so those patients who died during this hospital admission have 0 probability of readmission. So we need to remove those records. So the feature, that is discharge disposition ID containing the value 11, signifies that the person was died at the time of admission. So we will be dropping such records having discharge disposition ID equals to 11. This is the code for that. Also the feature gender has only 3 missing or invalid values, so we have decided to drop these records. Now let's run this code. Again we are dropping some columns with too many missing values, like you have already gone through weight, feature, payer code and medical specialty. So we are dropping these columns as they are having 60 to 70% missing values. Also we have noticed that the drugs named sitagliptin and examide, it contains same value throughout the column, so we will be removing these 2 columns as well. So now we are coding the non-numeric values, that is the feature change contains 2 values, that is CH for the medications changed and no for the medications not changed. So we are having 2 values over here, 0 and 1. Again for gender, for male we have used 1 and for female we have used 0. Again for diabetes medications feature we have used 1 for yes and 0 for no. Now let's come to age. So for age interval 0 to 10 to 9 to 100, we have coded it from 1 to 10. Like this is the code for that. We have replaced the range, that is 0 to 10 to 1, 10 to 20 to 2, like this and so on. Let's come to another code. Again, the dataset contains 23 features for 23 drugs, which indicate for each of these whether a change in that medication was made or not during the current hospital stay of patient. So medication change for diabetes upon admission has been shown by previous research to be associated with lower admission rates. So we decided to count how many changes were made in total for each patient and declared that a new feature. So the reasoning here was to both simplify the model and possibly discover a relationship with number of changes regardless of which drug was changed. So in Python, this is done by this code. So we have created a list of all those 23 features, and we have applied the code over here, that is the medications should be changed or not, like you can see over here, no or steady. So to check the result of doing this, we have used value counts over here. So you can see the output over here. Again, we are having 4 values there, that is in these features, in these 23 features, that is no, steady, up and down. So we have re-encoded all those features into 0 and 1. If there is no medical changes, then the value is 0, and we have combined all these values like steady, up and down into 1 just to balance the data set. Again, in this part of code, we have reduced both A1C test result and glucose serum result into categories of normal, abnormal, and not tested. So in A1C result, the values greater than 7 or greater than 8 signifies normal test result, so its value is 1. We have replaced the value of normal as 1, and for normal value, sorry, this one is the abnormal value, that is greater than 7 and greater than 8, that is the abnormal value, so we have coded it as 1. We have coded the normal value as 0, and not tested value, that is none, as -99. And same goes for this as well, that is max glu serum test result. Greater than 200 or greater than 300 are the abnormal values, so we have categorized it into 1. Normal value, we have replaced the normal value as 0, and not tested value as -99. So in this part of code, we have displayed the total number of medications used by the patient. So we have created another feature by counting the medications used during the encounter. So it contains key list which we have created, that is the list of 23 drugs. And to check the output, we can use this code, that is value underscore counts function. So this is the output for that, for checking the total number of medications changed. Now we have created additional columns for diagnosis for further steps. So we have categorized diag 1 into 2 levels, that is level 1 diag 1 and level 2 diag 2. Diag 2 into 2 levels, that is level 1, level 2, and same with the diag 3, that is level 1 and level 2 diag 3. Since all these diagnoses had 700 to 900 unique ICD codes, and it is extremely difficult to include them in the model and interpret meaningfully. Therefore, we have collapsed these diagnosis codes into 9 disease categories in an almost similar fashion to, to that done in the original publication using this dataset. So these 9 categories include circulatory, respiratory, digestive, diabetes, injury, musculoskeletal, genitourinary, neoplasm, and several others. Also, we have decided to use only the primary diagnosis in our model, since we are mapping the disease codes to certain category names. So this is the code which demonstrates it easily. So after creating a duplicate of diagnosis column, like over here, what we have done over here, we have recoded the disease codes starting with V or E, that is the disease codes which starts with variable V or E are in other category, so we have recoded them to 0. You can see over here. Also in this part of code we have replaced the unknown values with -1. Again we have changed the data type of all those features into float using ASType function. Now in this particular code we have iterated and recoded the disease codes between certain ranges to certain categories. Like I have already discussed about the ICD codes. You can search it over the internet that for every disease there is an ICD code, and it ranges up to 700 to 900, and this is what we have done over here. We have taken a particular record, and from values 390, and we have taken a particular range to which we can re-encode the values, like the values between 390 to 460 in level 1 diag1. We have recoded it into 1, and again we have recoded another values to 2, then 3, then 4, and so on. This is the code for that. In another part of code as well we have done the same thing, that is this is for level 2 diag1, that was for level 1 diag1, and this is for level 2 diag1, level 2 diag2 as well, and level 2 diag3 as well. So now just to check the output, we are done with this, and just to check the output you can display the header, that is you can display the feature, that is diag1, in a horizontal manner using .t. So this is the output which we have got, that is diag1 and level 1 diag1. You can display all the 3 diagnoses like this, that is diag1, diag2, diag3. Again in the last part of the code we have to save the work done so far into a CSV file as backup, so it can later be loaded from this point without needing to do all the above steps. I'm done with this video now. I will continue with the next tutorial in the next video, so stay tuned.